The universe is 13.8 billion years old. Before that, nothing. No space, no time, no matter. Everyone accepts this. But what does before even mean if time didn't exist? What caused the Big Bang? Where did it happen? What was there 1 second before it occurred? The standard answer is that time began at the Big Bang. But that's just restating the question with fancier words. It doesn't explain anything. Hawking's answer doesn't add something before the Big Bang. It removes the question itself. It changes what before means. The reason has nothing to do with what came earlier. It's about what time is when you look closely at the boundary. But everyone asks it anyway. What was before the Big Bang? The question feels natural, obvious even. And that's the trap. When you ask what was before, you're already assuming time extends backward infinitely, that there's always a previous moment, always something earlier. You're smuggling in an assumption that before makes sense here. It's like asking what's north of the North Pole. The question uses words correctly, follows grammar, sounds reasonable, but it contains its own mistake. The framework is wrong. The question feels natural because we experience time as flowing, one moment after another, stretching into the past. So of course there must have been something before, right? Wrong. Let's be precise about what we actually know. The universe is expanding. Galaxies are moving apart from each other. We can measure this. The light from distant galaxies is redshifted, stretched out because they're receding from us. Now run the film backward. If everything is moving apart now, it was closer together in the past. Keep rewinding, closer, denser, hotter. About 13.8 billion years ago, everything, all the matter, all the energy, all the space, was compressed into a single point, a singularity, infinite density, infinite temperature. At that boundary, Einstein's equations break down completely. Physics stops making predictions. The math spits out infinities, which means we're asking the wrong question with the wrong tools. The equations aren't hiding something mysterious. They're telling us we need to think differently. So, what are the right tools? First, understand what time actually is. Time isn't a stage where events happen, some absolute background ticking away independently. Time is physical. It warps, bends, dilates. Near massive objects, time slows down. This isn't philosophy or metaphor. It's measured. GPS satellites have to correct for time dilation, or they drift kilometers off course every day. At the event horizon of a black hole, from an outside observer's perspective, time stops entirely. A falling object appears frozen there forever. Time behaves like space. You can curve it, stretch it, compress it. Space-time isn't a metaphorical combination of two separate things. It's a single geometric structure. Einstein showed this a century ago. When you move through space, you're also moving through time. They're woven together. And geometry can do surprising things. It can close on itself. Which means at the Big Bang, where space-time curvature becomes extreme, we need to think about what time means in that regime. As you approach the Big Bang, backwards in time from now, space-time curves more and more severely. Temperature rises. Density rises. Classical physics, Einstein's general relativity, predicts a singularity where curvature becomes infinite. But quantum mechanics must kick in at tiny scales. There's a fundamental limit to how small you can probe space-time. The Planck length, about 10·35 meters. The Planck time, about 10·43 seconds. Below those scales, space-time itself becomes fuzzy, uncertain, quantum. You can't ask about precise moments or exact locations. The questions lose meaning. It's like trying to pinpoint the exact position of an electron. It doesn't have one. The electron is a wave of probability. Similarly, at Planck scales, space-time is a quantum foam of possibilities, and this fuzziness changes everything. In 1983, Stephen Hawking and Jim Hartle proposed what they called the no-boundary model of the universe. The key was using something called imaginary time, not science fiction, a mathematical technique where time is treated as an imaginary number. In this formulation near the Big Bang, the distinction between time and space blurs. The time dimension gradually becomes space-like. Imagine you're standing at the equator and you walk north. North has a clear meaning. It's a direction on the curved surface of the Earth. You keep walking north. As you approach the North Pole, what happens? You reach the pole, and suddenly north becomes meaningless. Every direction from the North Pole is south. But nothing dramatic occurred. The Earth's surface didn't develop an edge or a boundary. It just smoothly rounded off. The surface is finite. You can't walk forever, but it's unbounded. There's no edge to fall off. Now add 2 more dimensions to that picture. Well, not exactly 4 dimensions as we experience them, 4 dimensions in this imaginary time formulation where the math actually works without infinities or singularities. The universe's space-time could have the same property as Earth's surface. Finite in extent, but with no boundary. When you ask what happened before the Big Bang, you're asking a question like, what's north of the North Pole? The question uses the wrong conceptual framework. It's not that there's some mysterious answer we haven't discovered. The question itself dissolves when you understand the geometry. Time doesn't extend infinitely backward to some cosmic starting gun. Instead, as you go back toward the Big Bang, time rounds off smoothly. It becomes space-like. There is no edge, no moment of creation, no before. The universe is self-contained. Think about Earth's surface more carefully. It's 2-dimensional if you ignore thickness. You can specify any location with just latitude and longitude. The surface has finite area, but no boundary. You can't ask what's beyond the edge of the Earth's surface because there is no edge. Now imagine space-time like that, but with 4 dimensions instead of 2. This is what Hawking and Hartley proposed. The universe's history forms a closed 4-dimensional surface, finite but unbounded. When you try to go before the Big Bang, you're like someone trying to go north of the North Pole. The direction doesn't exist, not because something stops you, but because the geometry doesn't extend that way. Einstein once said the most incomprehensible thing about the universe is that it's comprehensible. But he also showed that time isn't what Newton thought, an absolute background. Time is geometry, and geometry can close on itself. Curiously, this makes the universe self-contained in a very precise sense. Consider the traditional argument for a creator. Everything that exists has a cause. The universe exists. Therefore, the universe must have a cause, God, or some external force that brought it into being. But wait, if time itself begins with the universe, causation begins too. Cause and effect are relationships that happen in time. A cause precedes its effect temporally. You can't have a cause before time exists, because before requires a time dimension to point backward in. Actually, more precisely, there's no before, not because we don't know what happened there, but because the concept doesn't apply. The question is malformed, like asking, what's the married status of the number 7? It's a category error, not missing information. The universe can be genuinely self-contained. No boundary in space-time, no moment when it began, no need for something outside time to create time. This isn't atheism as an ideology. It's a mathematical consequence of taking general relativity and quantum mechanics seriously. The equations allow a finite universe that's unbounded in time, a universe that just is, without requiring external initial conditions or a first cause. When Hawking wrote his famous line, "What place, then, for a creator?" he wasn't attacking religion. He was pointing out that the scientific model is complete without that hypothesis. The geometry works. The universe contains its own explanation. You don't need to add anything outside it. Whether God exists is a different question, one outside the scope of physics. But the question, What caused the universe to begin assumes the universe had a beginning in the sense of a first moment with something before it. And that assumption is wrong. But wait, doesn't quantum mechanics tell us that particles pop in and out of existence? Doesn't that mean something can come from nothing? Here's where it gets subtle. In quantum field theory, what we call vacuum isn't actually empty. It's seething with virtual particles that appear and disappear constantly, borrowing energy from the uncertainty. Principle: they can't stick around. You can only borrow energy if you pay it back fast enough. But these fluctuations are real. We've measured their effects. The Casimir effect, where two metal plates in a vacuum attract each other because virtual particles push them together. The vacuum has structure. Nothing in physics isn't pure philosophical absence. It's quantum foam, space-time itself fluctuating at the smallest scales. And in that context, a universe can quantum tunnel into existence, not violating any laws, just a natural process, one possible fluctuation among many. The probability isn't zero. Over vast stretches of imaginary time, remember, we're using this mathematical formulation where time becomes space-like, quantum fluctuations that produce universes become not just possible, but expected. No, wait, better to say it this way. In this framework, creation loses its usual meaning. The universe doesn't come from anything. It doesn't emerge at a specific moment. It simply is a consistent solution to the equations of quantum gravity. A self-contained geometric structure, finite but unbounded, requiring no external cause, because causation is something that happens within the universe's space-time, not outside it. Which brings us back to the original question. We started with what existed before the Big Bang. That question assumed before makes sense, that time extends infinitely into the past, that there must have been something earlier. But time is a physical dimension, part of space-time geometry, and that geometry can close on itself. Near the Big Bang, time becomes space-like. There's no boundary, no edge, no before. Asking what came before the Big Bang is like asking what's south of the South Pole. Not that the answer is mysterious or hidden. The question uses the wrong conceptual framework. The geometry simply doesn't work that way. And this isn't just speculation. We've measured the cosmic microwave background, the radiation left, over from about 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely. The patterns in that radiation, the tiny fluctuations in temperature across the sky, match the predictions from inflation theory. Inflation requires quantum fluctuations in the early universe to be stretched out to cosmic scales. Those predictions work best with models where space-time has no initial singularity, no moment of creation, just a smooth boundary where time rounds off. The data fits. GPS satellites prove time dilation every day. Black hole observations confirm that space-time curves exactly as Einstein predicted. General relativity plus quantum mechanics, combined correctly, gives us a universe that's finite in the past but unbounded. No edge. No beginning in the conventional sense. The universe contains its own explanation, not because physicists are clever, but because that's what the geometry allows, what it seems to require actually. There's no gap where you need to insert an external cause. The laws of physics are sufficient. And that changes something fundamental about how we think. If the universe needs no external cause, it's genuinely self-explanatory. Initial conditions aren't arbitrary choices that some external agent made. They're the only smooth solution to the equations. The universe is what it is because that's the only consistent way for it to be. Think about the anthropic principle for a moment. We observe a universe compatible with our existence. And people sometimes treat this as a shocking coincidence. Out of all possible universes, we got one with the right physical constants, the right laws, to allow stars and planets and life. But if we're here, of course, we're observing a universe compatible with our existence. We couldn't observe one that doesn't allow observers. It's a selection effect, not a coincidence. The mystery isn't that we find ourselves in a life-friendly universe. The mystery would be finding ourselves anywhere else, which is logically impossible. When Hawking gave lectures on this in the 1980s, religious audiences sometimes objected. They felt he was trying to eliminate God from the picture, but that wasn't his intent. He was showing that the scientific model, the mathematical description of how the universe works, is complete. It doesn't have gaps that require external intervention. Whether God chose these particular laws of physics, whether there is some deeper metaphysical reason for existence itself, those are questions outside the scope of science. Science describes how things work, not necessarily why there's something rather than nothing. But the how is complete. There's no missing piece where you insert, and then God caused the Big Bang. Actually, we've moved the question, not what caused the Big Bang, but why these laws of physics, why quantum mechanics, why general relativity, why a geometry that allows this no-boundary solution. Those questions are deeper, possibly unanswerable by science because science uses these laws to explain other things. You can't use the laws to explain themselves without circularity. Maybe there's a multiverse, an infinite collection of universes with different laws, and we're in one compatible with observers. Maybe there's some deeper principle that selects these particular laws. Maybe, and Hawking acknowledged this, the question, why is there something rather than nothing, is simply beyond physics. We don't know. But what happened before the Big Bang, that one we can answer. There was no before. There was no moment of creation, no starting point, no first instant of time. The universe is finite in temporal extent. You can't keep going back forever, but it has no boundary, no edge, no beginning. Time itself is part of the physical universe, and it rounds off smoothly as you approach what we call the Big Bang. The question, what existed before, assumes a framework, absolute time extending, infinitely. That doesn't match reality. It's not that we're avoiding the question, it's that the question dissolves when you understand what time actually is. Time is a dimension of a four-dimensional geometric structure, and that structure is closed, finite but unbounded, self-contained. But that raises a deeper question, one Hawking knew he couldn't answer. Why these laws? Why quantum mechanics with its uncertainty principle? Why general relativity with its curved space-time? Why a universe where the no-boundary proposal even makes sense? You can ask, why is the universe the way it is? And that's a different kind of question. Maybe there's a multiverse with different laws in different regions, and we're in one where intelligent observers can exist. Maybe not. That's speculation. We don't know. But what happened before the Big Bang? That question we can answer. There was no before. The universe is self-contained. The question itself doesn't make sense once you understand the geometry. I've got to stop somewhere. But think about what this means for how you picture time, not as an infinite river flowing from the distant past, but as something physical that can bend, curve, close. And at the boundary we call the Big Bang, it simply rounds off.